Hi guys, welcome to the video series again of investigating or introducing us to the nuclear material phenomena in nuclear environments. So welcome, and today we want to talk about the incident neutron producing the primary knock-on atom, or pKa. Now previously we've assumed simplistically that all neutrons hitting the atoms, they come in at about 1 MeV. And this is a very simplifying assumption to estimate damage. However, neutrons, they don't just come in at 1 MeV, they can come in at a spectrum or distribution of energies, ranging from very low energy to a very high energy. And depending on their energies, they will do more or less damage corresponding to their individual energies. So if you have, let's say, these three neutrons, one at about 14 MeV, one at about 1 MeV, one at about 50 keV. Which one is going to do more damage? Usually it is the 14 MeV neutron, because it has so much energy that it can knock off more atoms from their lattice sites, and that will cause more displacement damage overall. And so even if we talk about a neutrons coming in with an average energy of 1 MeV, you know that this is a statistical distribution. Some are going to come in slightly faster than 1 MeV, and some are going to come in at slightly slower. And previously, based on our simplified model, simplified model, all neutrons at 1 MeV. So the simplified model, all neutrons coming at 1 MeV, the dPa, the displacements per atom we calculated, was about 3.77. However, if we were to take into account this spectrum effect, how is that going to affect our damage estimation? So you're going to have some coming in at a higher energy, some coming in at a lower energy. So how is that going to how is this going to this is a spectrum, the neutron spectrum. How is the neutron spectrum going to affect damage estimates? Okay, so today we want to attempt to capture the effect of the neutron spectrum by calculating some averaged cross-section for displacement over various neutron energies. So this is known as the displacement cross-section. So this is the chance, well, if you use the cross-section analogy, this is the chance that, or the probability that the neutron will create one displacement. This is not the pKa. This is not the pKa. This is creating displacements. So in a displacement cascade, you have many atoms being displaced from their lattice sites. Okay, many atoms displaced. So the displacement cross-section will measure the probability of displacing one atom. So it's not the whole displacement cascade, but it's just displacing one atom. Okay, so how can we define these spectrums? Well, there are two broad categories of spectrum. One is the thermal spectrum, and one is the fast spectrum. Okay, so how do we define what is the thermal and what is fast? Well, for starters, we must remember that temperature and kinetic energy are related. at the particle level. So with a higher temperature, we have a higher average kinetic energy. So a higher temperature often means that the particle is faster. So higher temp, higher kinetic energy. So when we talk about thermal means it doesn't necessarily mean that it's hotter. It just means it is in thermal equilibrium with environment. So, and the fast spectrum is anything so-called faster than this thermal equilibrium. Okay, so if you want to go put in some numbers to that, sometimes for the average kinetic energy of a fission reactor, there will be about 1 MeV. It's a fast fission reactor. And then 14 MeV is a fusion neutron, where you have a DT, deuterium-tritium reaction. That will be a fusion reactor. So in terms of neutron damage, which one's more harmful? It will be this fusion neutron. And these are the fastest neutrons you'll probably find in most conventional nuclear reactors that we are discussing. So let's put some numbers to the neutrons we are discussing. So when we talk about the thermal spectrum, now this is what most light water reactors would use, because when you decrease the energy of the neutron, the cross section for fission will actually increase. So that's what happens in a thermal reactor. And the way to slow down the neutron from a fast to a thermal spectrum, so slowing down of neutrons from fast to thermal, this process is called moderation. Okay, so this process is called moderation, and very common moderators we use are water and graphite. So these are just some common moderators. So this will basically help the neutron reach thermal equilibrium with the environment. So what does the spectrum actually look like? If you were to look at the flux distribution, so this is the flux at a certain energy of the neutron, En, it will look something like this. So the peak will be at 0.025 eV. So there should be a peak there. Okay. The peak is here, or somewhere there, quite near there. And it will dip according to the Maxwell Boltzmann distribution. So if you're interested about what the Maxwell-Boltzmann distribution is, I'm going to leave a PDF in the comments for us to see, what the Maxwell-Boltzmann distribution is and where it kind of stops, where this peak kind of stops. So for simplicity's sake, I'm just going to assume that you already know that, or we can just simply say the peak will dip way before 0.1 MeV. So if you're talking about thermal spectrum, you'll barely find any neutron that has an energy above 0.1 MeV of energy. So there's hardly anything there. So what we may define as fast, some people's definitions may differ here and there. Maybe we can talk about 0.1 MeV or more, and that can be defined as a fast fast spectrum. Okay, So if this is the flux as a function of energy, then a fast flux can be defined like this. The total fast flux equals to the integration from 0.1 MeV to infinity in terms of the neutron energy, phi En dEn. So that's just taking all the area under the curve, except it's over here. It must be somewhere here rather than here. If you're integrating this part, then this will be the thermal flux. So thermal So these are just two very broad categories. So one can, kind of say something like this. But this is a very unrefined way, a very approximate way of describing this, because actually in between these energy ranges there are other energies as well. Some people may call it epithermal and all that kind of stuff, but for our intents and purposes we'll just leave it as this for now. Okay, so so what is the kinetic energy distribution of the fast spectrum? So how can we estimate that? Now this we have to look at how fission neutrons are made. Okay. We have to look at how fission neutrons are made, especially when these are released over fission fragments. Released when the fission fragments from freshly split uranium-235. Okay, so if you have a uranium-235, and then we'll split into two fragments. Okay. Then they will start to emit neutrons. And this will range at about plus or minus 1 MeV. And to actually have this aggregate, we'll need to do lots of calculations as to the statistical distribution of these individual fission fragments and the neutrons they emit. So if we were to try and calculate this, we will need to know the statistical distribution of products. So usually this probability versus atomic mass. So usually the fission product distribution will be in this shape. So that will tell you the probability of these fission products. Then we will have to get these neutron energies coming from each of these elements and then kind of do an integration of what the neutron energies will start to look like. So you can imagine that is a very complicated thing. So if you just to do it simply, okay, if you just to do it simply, we'll have something like this. This is an approximate shape. Yeah, most of them will come at a less than 1 MeV. Some of them will go over 1 MeV. Why is it not symmetrical? That depends on the energy level. Okay, so this is phi En, this En. Now that depends on the energy levels when the neutron is emitted. So usually, if you have a very high energy nucleus, okay, and it's just come off fission, so you can imagine the thermal energy will be spread across all the nucleons, the protons and neutrons in the nucleus. And of course neutrons will be the first to come off because there are so many of them. Okay, So if the energy is evenly split, and then one of the neutrons come off, okay, one of the neutrons come off to kind of take away most of the energy, this will be the energy taken away equals to the neutron separation energy plus maybe this 1 MeV. That depends on how much energy is here. If you want to jack this up, by maybe like going to 8 MeV, well, that kind of doesn't make sense. Why is that? Why doesn't that happen? Because the neutron separation energy is about 6 to 8 MeV. If you have a 8 MeV neutron that's coming off this nucleus, that's very unlikely. What may happen instead is that you will have 2 of these neutrons coming out instead. So there will be 2 1 MeV neutrons. So the more energy you pump into this nucleus, the more neutrons kind of get to come out. So there is some upper limit to this energy here. But of course, if you talk about lower limits, then yes, there are many of these here. So this is why why this thing is not quite symmetrical. Okay, and yeah, and of course it doesn't go all the way up to 8. All right, so that explains why there is this kind of limit. And there are other factors like energy levels available in the atom, like the states and everything, but this is a nuclear physics phenomena which I won't discuss in detail. So what about fusion neutrons? Fusion. Okay, so this is about the 14 MeV. Yeah, fusion neutrons usually come out at about 14 MeV. But of course, as they, in this fusion reactor, we talk about a fusion reactor in a tokamak, where there's a lot of plasma. So the neutrons, it may not necessarily go all the way through without colliding with anything. They can collide with the plasma, and their energy will start to decrease. So that's why you have this kind of a shape here. So you still have less energetic neutrons because of the scattering that happens inside the plasma or in some other atoms. Also, all in all, we know that there are different neutron energy spectra, and these can cause different effects on our material. And usually, if you have looked at the cross-section video we have discussed before, you have seen the cross-section look something like this. So this is a sigma, and then this is energy of the neutron. Okay. If you look at the cross-section video, you look at something like this. Basically, it means with higher neutron energy, the cross-section for, let's say, scattering, it will decrease. And this is because of some quantum physics phenomena. And all this will actually play a part in how many pKa's it can, how much damage it can make per unit volume. So let's put all this in some diagram and try and do some mathematical derivation as to kind of find out an expression for damage. So let's consider a neutron with energy En. Okay. And then, so this is just one of the energies in this spectrum. This can be a lot of energies. This is just one of those energies. Okay. And not only do we have a spectrum of energies coming out, the neutron can look at this pKa and it'll scatter at various angles. And remember that if it scatters at, let's say, an angle closer to 180 degrees, this pKa will have more energy. If it scatters at an angle less than 180 degrees, then this pKa will have less energy. Now that further complicates things yet another level. And this is what the displacement cross-section also tries to take into account. Now, actually, yeah, displacement cross-section takes all these effects into account. Displacement cross-section actually takes all these things into account. It doesn't take into account the energy spectrum. So displacement cross-section takes care of the second part. The neutron spectrum, this one we will have to do some integration. So this is an energy spectrum. Knowing that neutrons can come in at various energy. Maybe one that comes in at 0.8, one comes in at 1. And then let's say this is fixed. We take in one representative energy. We try and calculate the overall effect of how much energy it transfers to the pKa. That will be the displacement cross-section. So correction to what I mentioned earlier. Yeah, displacement cross-section, it talks about the probability of displacing one atom given one neutron energy. Okay, so you can imagine the forget my mistake. Yeah, please forget what just now I was discussing. So we have displacement cross-section that's calculating damage based on one neutron energy, and then this will have to be considered alongside the fast and thermal spectrum considerations we were talking about before. Anyway, let's move on. All right, where were we? Yes, so now we have to take into account all these angles and the various energies transferred to this pKa. So how can we do that? Well, firstly, we'll have sigma n, En, and T to describe the cross-section. Okay, so this is the cross-section of a neutron with energy En transferring energy T to this pKa. Okay, so this is a neutron again. Neutron sigma n, cross-section of the neutron with energy En transferring energy T. So at different angles, different energy is being transferred. So if we were to take one of these energies, one of these angles, let's say with theta and T, okay, this is the cross-section based on this specific energy being, this pK with this specific energy being generated. Now, if we want to calculate the scattering cross-section that we have talked about before in the NNDC thingy, so if we were to relate it to the scattering cross-section, that will simply be from 0 to lambda En sigma n E n T d En. Oh, sorry, this should be dt. Okay, anyway, what are we talking about here? We're talking about the total interaction probability of this neutron across all energy. So this is the scattering cross-section. So I don't care what energy is being transferred to this pKa. I just care what's the chance of this neutron interacting with this atom. And we can see that the amount of energy transferred to this atom, it ranges from 0 to the maximum, the lambda En. And we have discussed what lambda is before. Lambda equals to 4m m over m plus m squared. Now in this case, the neutron mass is 1, m is whatever mass you're talking about, and if we take m is more than the neutron mass, the mass of the pKa is much greater than the neutron mass, we can just assume that this m plus m, okay, m plus m is approximately m. So let's again write this here. Lambda equals to 4mm over m plus m squared. So 4m much bigger than m. So the capital M bigger than m. So this is just 1. Okay. M plus 1 is equal to, or approximately equal to m. So if this is iron, this is 57, and that is approximately equal to 56. It's just a mathematical approximation. So let's look at the lambda. So it's 4 times 1 into m over m squared. So 4m over m squared, that's just 4 over m. That is what our lambda is approximated to. Okay. So the maximum energy is again lambda, capital lambda En. That's the maximum. And yeah, that will help to determine the scattering cross section. So this is kind of the interaction cross section of the neutron En giving energy T to this pKa. This is the scattering cross section. Now if you want to consider the various energies of this pKa and how many displacements it will create, so again, similar concept. I kind of mix things up a bit, but similar concept. If a pKa has higher energy, it's going to cause more displacements. Alright, so higher energy pKa, it means more displacement. So how are we going to consider this effect? So we can look at the displacement cross-section, which we are trying to calculate now. And then this will be the integration of the neutron coming in and giving this energy T. And if it does so, it will generate the number of displacements, Vt, where V is the number of displacements depending on energy T of the pKa. So that is into dt. So what's the minimum energy for displacement? That is Ed, because it doesn't make sense to integrate from 0, because you can't the displacement cross-section from 0 to Ed is just 0, so we just ignore that. The maximum energy of the pKa is lambda En. So that is the displacement cross-section. Now that's fine and all, but how do we then define this term? We can make another simplifying assumption. Okay, so simplifying approximation for sigma n En T. Okay. So since we have cross-section data for scattering already, okay, so we already have scattering cross-section data, and that is the integration from 0 to lambda En sigma n En T dt. Since we have this already, what we can assume is isotropic scattering. Assume isotropic scattering. What does that mean? It means that regardless of the energy, regardless of T, the probability of the pKa with energy T, the probability of the pKa with energy T is the same. So if we were to plot this in a graph, you'll see something like this. So we have the energy of pKa, T, and this is probability of pKa with energy equals to T. So this is just some notation I'm using. It's not official. And then this is the energy T. So we are assuming it's a flat distribution. So that's what isotropic scattering is talking about. Now, strictly speaking, this is not quite correct because of diffraction, resonance, etc. And these are quantum mechanical effects. But for our intents and purposes, let's just ignore that for now. So our neutron scattering cross-section at energy T becomes this value divided by the energy range. Okay? Okay, so let's write this down in a very more formal or more neat looking way. Okay, so sigma n E n T, alright, that is equals to from 0 to lambda E n sigma n E n T dt over lambda E n minus 0. And since this is a scattering cross section and this is just the bottom, sigma s E n over lambda E n. Now we have something much more palatable and we can work with it. And it's independent of the energy transferred to the pKa T. Okay. So since we have that, let's chuck that back into our displacement cross-section expression. So we'll have something like this. Okay. So that's what we have. Now, since this doesn't depend on T at all, we can just get this out. Now, this one, well, that depends on the kinchin-pease model now. We have seen the kinchin-pease model that tells us that the number of vacancies or displacements created depends on the energy, and there's some threshold energy where the more you increase the energy, the more displacement you make. But after a certain threshold, and this threshold is EC, okay, this threshold is EC, and this is E of the pKa. Oh no, this is not E of pKa, this is number of displacement, and this is E of the pKa, ED, EC. Okay, the maximum here will be T equals EC over 2 UD. After this threshold, this will be 1. Because with displacement energy, you can only displace 1. So there's nothing much to talk about there. So this integral, we can split it into 2 parts. Okay, so we can integrate from ED to EC. And we can integrate from EC to infinity onwards. So this describes, this one will describe this regime here. And this part here will describe this regime. So this is T equals to infinity. Okay. Or rather, it should not be infinity. This is just lambda En. So this will describe this regime here, which is the electronic stopping regime. Alright, so let's do the first part. First part is this, and that will be, according to our kinchin-pease model, T over 2 ED dt. And now if we were to integrate, that will become t squared over 4ed, ed to ec. Okay, so now that's all we have, ec squared over 4ed minus ed squared over 4ed. Well, as you can see here, ec squared is much bigger than ed squared. So the approximation, well, we can just ignore this bit for mathematical simplicity. Alright, next. Okay. So next, we want to look at this part. So this is the other regime, and that will be equals to T times EC over 2ED, EC to lambda En. Okay, and that will be equals to simply this. Okay, now we just substitute this back into our displacement cross-section. Is equals to the sigma scattering En over lambda En. Okay, that's the first part. Okay, can you see? First part. Then this integral we split it in two. So we need to add in both the terms that we have just derived. So the first term is this, EC squared over 4ED plus EC lambda En minus EC over 2ED. And that's how we find our displacement cross-section, assuming isotropic scattering. And of course, we assume that the kinchin-pease model, that holds. Okay, so that's all I have for you for this part of displacement cross-section. Again, apologies for the mistake earlier. Yeah, but do note that displacement cross-section, that depends on neutron energy, but it takes into account the multi-directional scattering of this pKa. It is not the neutron we are talking about. If you are to look at the neutron itself, then we will have to look at another angle, which will, rather, we have to develop another expression, which we will carry on in the next video. Thanks for watching. See you guys again. Bye bye.